So we meet once again, and for some fun-filled session. I'm not going to burden you. Let's enjoy this interactive session. I don't want it to be a monologue. Uh, what I want to informally offer to you is integer solutions to equations. Now, as of now, what have you learned? Someone gave you x plus y equal to 5 and said find all possible pairs x comma y that satisfy this equation. Infinite sets of x and y will satisfy this equation, right? However, if you had knowledge of the physicality of the situation, if someone told you x represents the number of monkeys in the class, y represents the number of donkeys in the class, then you know for sure x and y have to be whole numbers. There could be no monkeys, there could be no donkeys, so 0 is included, right? So then, if someone committed to you that, well, x and y fundamentally represent the number of monkeys and number of donkeys in the class, then x and y cannot be negative, and x and y have to be integers, right? You can then reduce the number of solutions to the following. Number of solutions to this equation then could be reduced to the following. You could have had x equal to 0, no monkeys, all donkeys. You could have had 1 monkey, 4 donkeys. You could have had 2 monkeys, 3 donkeys. You could have had 3 monkeys, 2 donkeys, 4 monkeys, 1 donkey, 5 monkeys, no donkey. Right? This then is supposed to be the number of integer solutions to this equation given the set of constraints. Clear? Now, this entire business of finding integer solutions to equations is a very elaborate thought. There is a lot of sophistication in it. Especially, there is a lot of literature which will tell you number of integer solutions to an equation of the kind ax plus by equal to c, where a, b, c are integers. The number of integer solutions to ax plus by equal to c will fall within the jurisdiction of a very special treatise. I'm not going to jump into that right away. What I want to offer to you is something which is within your reach, something that you would enjoy while you're doing. It might involve small little manipulation here and there. This would be your first stint of exposure to finding integral solutions. All right. Now, informally, there were three fundamental things which I thought were important in terms of actually solving for integer solutions, which is why I classified these problems into 3 categories when we have to find integer solutions. One, of course, you find there is observing the situation, observing the equation, looking at parity, the even-odd situation, looking at divisibility issues. Some of these issues would lead us to integral solutions to equations. The second one is factorizing. Factorizing could come in very handy. Now, I have a remark here. One expression which I feel we encounter very often, and learning how to deal with that expression would be cardinal. Therefore, instead of holding on to that, let me unleash that expression and tell you how to deal with that expression as and when that expression appears, so that from this point onwards, you could look upon that expression as a standard template and you could deal with it. All right. The expression of this kind in x and y, xy minus x minus y, an expression of this kind, I reckon, would be a very commonly occurring expression. And let me share with you how to deal with this expression. If you have to break it up into factors, or you want to condense this expression, the manner in which you should deal with this expression. Now, realize that from these two terms, I could take x common, right? So if I took x common from these two terms, I am left with x into y minus 1. How about it? Right? Now from this term, minus, what I do is, it would have been so nice if this was also y minus 1. It would have been really nice if this was also y minus 1. Does not matter. If it's not y minus 1, I can impose a y minus 1 like this. Now in the process, what I have done is, I have added 1 to this, isn't it? In the whole expression, I have essentially added 1, and I must balance it. I must therefore subtract 1 from it. I must therefore subtract 1 from it. Right? Which means, now, I can potentially take y minus 1 as a common factor. So if I took y minus 1 as a common factor, then I am left with x minus 1 inside, and then there is a unattended minus 1, there is a unattended minus 1. What do you say? Right? Every time you encounter an expression of this kind, I'm not saying this is what you have to do all the time, but my take on it is, 9 out of 10 occasions, an expression of this kind would require you to express and condense the expression in this format. It would be particularly handy to do that. Which means, just to transpose the terms, and rewrite this expression, that means transpose 1 on this side. Transpose 1 on this side. We end up getting 1 plus xy minus x minus y is actually x minus 1 into y minus 1. We are going to use this time and again. Look upon this, for the sake of our class, as a standard template dealing with an expression of this kind, right? Once you know how to deal with this, in addition to other ways of factorization that you have learned how to factorize using fragmenting the middle term in a quadratic expression, and so on and so forth, so many ways, or finding the values of x for which the expression becomes 0, factorizing that way, and so on and so forth. But then this expression, an expression of this kind, would really be useful, in our further digressions on the subject. Now, so like I said, an informal approach to finding integer solutions to equation would involve 3 fundamental categories. First category, where I said, observe, parity, divisibility. These 3 issues you can keep available at the top of your cranium, number 1. Number 2, factorizing. That's the second category of problems that you would encounter in an informal understanding of finding integer solutions to equation. And the third one is inequalities, which would be slightly more versatile and very much potent in finding integer solutions to equations. All right. Now, without really wasting time into too much of discoursing on the subject, let's get into the business of solving problems and see what to observe, how to observe, where to observe, where to attack. Let's look at all of this and get a feel, an inherent feel towards an informal understanding of finding integer solutions. Now, once I set this background for you of finding integer solutions to equations, informal background, then subsequently, in subsequent sessions, what I'll do is I'll try and help you mature to a more formal treatise on finding integer solutions. Okay, let's start getting tuned to the frequency of finding integer solutions to equations, right? Let's begin to tune ourselves to that frequency. That's the objective of this class. if I'm able to successfully tune you to that frequency, then I would have made you ready for a formal treatise on integer solutions to equations. So are we all ready for action? Right? Okay, let's start looking at the sheet. Integers, we love you. They are God sent. So the first category of problems that involves observation, parity, divisibility. Parity is about even odd, divisibility is about observing what divides a certain expression, a certain number, and drawing conclusions and inferences from there. Right, Supreet? Feel free to interact with me. Feel free to stop me any number of times. I'm at your service. Okay? So we have problem number 1, which says A, B, C are distinct natural numbers. A, B, C are distinct natural numbers. Right? And there are two other conditions given in the form of equations. One is 2a is b plus 2 and b squared is ac. And I want to find the values of a, b and c, or at least evaluate if a, b, c are obtainable, and if at all they are natural number values of a, b, c commensurate with this condition, also enjoying distinctness, a, b, c being distinct, being natural numbers and commensurate with these conditions. Now, in school, they would often tell you if you have 2 unknowns, you will require 2 equations. If you have 3 unknowns, you will require 3 equations. If you have 4 unknowns, you will require 4 equations. Let's start breaking loose from this traditional incorrect way of looking at things. I need to tell you that if there are, in this case, how many unknowns are there? A, B and C? Yet there are 2 equations. Now each equation should be looked upon as a condition. And in fact, for 3 unknowns, even though there are 2 equations, there is another condition in the form of settling with the fact that A, B, C are distinct natural numbers. So that essentially may not be an equation, that's not an equation, but that again is a condition, which when flushed with these 2 conditions might enable obtaining the values of A, B and C. In the first place, are you ready with this thought? Right? So then, first things first, looking at these 2, you get a little bit of a clumsy feeling. Hey, how on earth? It does not matter. The first thing that you have to do as an attempt to become an accomplished problem solver is be enterprising, be brave, be courageous. Take the first step based on the flow of the situation, and then down the line you will find that nature will oblige. Let's see if we are courageous enough, how nature begins to oblige solving this problem. Okay. Now, let me eliminate b from here. How do I eliminate b from here? This b I could write as 2a minus 2 from this equation. The b could be substituted as 2a minus 2 and could be plugged into this. That way at least one of the devils will get eliminated. Of the 3 ABC, one of them would get off. Yes. So what I want to do is the b that I obtained from here, which is 2 into a minus 1, could be plugged into this. Right? Let's do that. That's the least that we could do. In fact, that's the only thing that we could do ab initio, right? So b squared, which is like 4 into a minus 1 whole square, is AC. Yes or no? Right? Now, once we have this, let me say C would then be 4 divided by A into A minus 1 whole square. That's the only other thing we could do after this. What else? right? Nature has not left us with too many options, too many choices for this equation, right? Now, even if you could not see the problem to the very end, if you didn't even have an X-ray vision into the problem, go by what nature is suggesting. Now nature is suggesting, hey, try the next thing out. Expand a minus 1 whole square. Expand a minus 1 whole square. A squared minus 2a plus 1. Yes or no? Right? So let's do that. Take one thing at a time without feeling burdened about what's eventually going to happen. You have to be industrious, you have to be iterative, you have to be experimental in order to become an accomplished problem solver, right? So we'll take to that approach and see how it goes. Fair enough? Are you all fine with this idea? So then, what it leads to is 4 by a squared minus 2a plus 1. Right? Now, one of the things is, the C then has become a certain ratio. Has become a certain ratio. What fact have we not yet deployed in doing this algebraic manipulation? The fact that ABC are integers or ABC are natural numbers, that fact has not yet been injected into the system, right? So we now start to explore the prospect of flushing that thought with all of this. All right, let me see, this A is sitting isolated outside. Let me give it a little push, allow it to go in, allow it to go in. Let's do that, right? Because with this 4, it's looking like an odd man out. Let me push it in, right? When I push it in, then C becomes 4 into a minus 2 plus 1 by a. Yes or no? See, a minus 2 plus 1 by a is what becomes of it, right? Very mundane, ordinary manipulation. Now, this I could write as 4 into a minus 2 plus 4 by a. Yes or no? Now, let's start to, because see, no further manipulation is possible. We have exhausted all manipulation that was available. Khatam. We can't manipulate it any further. Now, we will have to start deploying the conditions given, right? Okay. Do you realize that if A, B, C are natural are integers, say, then 4 into a minus 2 will be an integer, right? 4 into a minus 2 will be an integer, clear? Now, C is an integer. C is an integer. So, 4 by a would have to be an integer. 4 by a would have to be an integer, yes or no? Because integer plus integer, that would be an integer. So, 4 by a would have to be an integer. Now, see, you'll realize that nature will not leave you unattended here. So, now, in order that 4 by a be an integer, a could have only how many values? 1, 2 and 4. 3 values, right? 1, a could be 1, a could be 2, a could be 4. A is a natural number. So, in order that a divides 4, a could have only 3 values. A could be 1, a could be 2, or a could be 4. Yes or no? Now, let us, so the entire set of natural numbers in A has been reduced to 3 values. Now, it's not going to be a tall order to explicitly examine these 3 and see which of the 3 is sanguine, right? We need to then authenticate 1, 2, 4 and eventually precipitate on which of them is right. Clear? Let's do all of it. Let me remove the clutter from here. Now that we have converged to 3 values, let's examine their authenticity. See, let me look at a equal to 1 and see if this could match the bill. When A is 1, see, put A equal to 1, you get B equal to 0. Isn't it? You get B equal to 0 from this equation. See, if you put A equal to 1, then 2 equal to B plus 2, so B then becomes 0. Hey, but B is a natural number. And what I get out of A equal to 1 is B equal to 0, which is not a natural number. So A equal to 1 is ruled out. A equal to 1 is inept. Right? Let me examine A equal to 2. Let me examine A equal to 2. So when I put A equal to 2, see, 4 equal to B plus 2, 4 equal to B plus 2, that gives me B equal to 2. So that gives me B equal to 2. Can I accept this value? No, why? Because they are meant to be distinct natural numbers. I'm getting A and B both as 2, so I will rule this out. I will rule this out. Sounds fair? And therefore, now if A equal to 4 also does not fit the conditions, then there are no values of A, B, C commensurate with the requirements. If I put A equal to 4, put A equal to 4, so 8 equal to B plus 2, B equal to 6. Good. For the first time, I am beginning to see light at the end of the tunnel, B equal to 6. Right? Now if B is 6, so far so good. Put B equal to 6, so 36 equals 4 into C, 36 equals A which is 4 into C, that gives me C equal to 9. Very good. All of it now is fine. C equal to 9. A will be 4, B will be 6, C will be 9. That's the set of ABC that satisfies all the conditions of the given problem. Does it make sense to all of you? Right? It does, isn't it? Okay. Let me illustrate a little more and get you into the groove. But so far so good. So what did this problem involve? Nothing special, just the confidence to explore and experiment. Look at a basic divisibility issue. It eventually boiled down to examining those natural number values of A for which 4 will be divisible by A. Eventually it got reduced to that, and then you had to explicitly look at the 3 values of A that will do that and rule out the ones that don't satisfy. Clear? Was it difficult? It was different but not difficult. It required you to in a very ordinary sense examine a simple divisibility issue. In the first place, ordinary manipulation, eliminating 1, and then the last step really involved a simple divisibility issue. Clear? Are you confused? No? Very good. I hope all of you understand what a factorial is. Do you understand what a factorial is? Where? Let's see. Let's see. Good. See, first of all, those of you who do not understand what factorial means, essentially when I talk of 1 factorial, it's 1. When I talk of 2 factorial, it's the product of the first 2 natural numbers, which is 2. When I talk of 3 factorial, it's the product of the first 3 natural numbers, which is 1 into 2 into 3, which is 6. When I talk of 4 factorial, it's the product of the first 4 natural numbers, which is 1 into 2 into 3 into 4, which is 24. When I talk of 5 factorial, product of the first 5 natural numbers, that will be 120. When I talk of 6 factorial, product of the first 6 natural numbers, that makes it 720, and so on and so forth. So in a very general sense, if n is a natural number, then n factorial would be 1 into 2 into 3 into 4 into n minus 1 into n. Yes or no? That's n factorial, right? That means the product of the first n natural numbers. Realize that if you exclude the last member here, then the first n minus 1 members is the product of the first n minus 1 natural numbers, and the product of the first n minus 1 natural numbers would be written as n minus 1 factorial into n. How about this? No? So n factorial could be written as n minus 1 factorial into n. As a special case, if you plug in n equal to 1 here on both sides, if you plug in n equal to 1 on both sides, then the left hand side is 1 factorial. The left hand side is 1 factorial. This will be like a 0 factorial. This will be like a 0 factorial. Put n equal to 1, so this is 0 factorial into n equal to 1, that is 1. Now that gives us 0 factorial equal to 1 factorial by 1. So 0 factorial is 1. So again, 0 factorial is 1. In fact, let me tell you, once we mature in the subject, factorials are defined not only for natural numbers, they are defined for whole numbers, they are defined for integers, they are defined for fractions, they are defined for irrationals, they are defined for everything. We have special functions that do that, but too early to break free into that domain. But then sooner or later we will generalize this entire view on factorials. But for the time being, it suffices if you understood this bit on factorials. Right? Now, in light of this, let's look at the next problem. Let's look at the next problem. So, in problem 2, we are talking of two natural numbers m and n. We are talking of two natural numbers m and n, satisfying where n is a natural number greater than 5. N is a natural number greater than 5. Okay. We are then talking of 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus 5 factorial plus 6 factorial plus n factorial is square of a natural number, n. And I seek to find natural number values of m and n. Okay. Now, once again, using conventional ways, there is nothing that I can do to explicitly obtain the values of m and n. Let's see first of all the feasibility of this condition. It's also important to check on whether this is feasible or not, whether m and n will at all subscribe to this condition. If m and n are natural numbers, let's see if m and n can at all subscribe to this condition. Okay. Okay. One thing, n is greater than 5, that means we'll have 5 factorial onwards, all the terms appearing. It could stop at 7 factorial, it could stop at 8 factorial, but for sure n could be 6, n could be 7, n could be 8, and so on and so forth. We do not know where. So for sure, in some of these factorials, 1 factorial, 2 factorial, these terms will certainly appear. 1 factorial to 5 factorial will certainly appear, isn't it? Because n is given to be greater than 5. So if that is guaranteed, let me see what this sum turns out to be. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, this much for sure. Yes or no? Okay. See, terms before 120, this is 30 and 3, 33. This is 33. Yes or no? Now, up to 5 factorial or up to 4 factorial, what's the units digit? 3. Now, after 5 factorial onwards, do you realize that every member in the product will have a 2 and a 5 for sure? 5 factorial has a 2 and a 5, so it will end in 0. Because in order to write 5 factorial, Supreet, I'll write 1 into 2 into 3 into 4 into 5. So in the product, there is a 2 appearing for sure, there is a 5 appearing for sure. So this must end in 0. 6 factorial, 1 into 2, into 3, into 4, into 5, into 6. There is a 2 appearing, there is a 5 appearing, right? So this must also end in 0. 7 factorial also will end in 0. 8 factorial will also end in 0. Yes or no? That means all factorials from 5 factorial onwards will end in zeros. Are you there with me? So everything from 5 factorial onwards will have a units place 0. Yes or no? And up to 4 factorial, the units place is 3, 24, 630 and 3, 33. So units place is 3. And for all others, the units place is 0, 0, 0, 0, etc. So then when I add all these numbers, what will be the units place of these numbers? 3. That's certain. That's certain. Right? That means the left hand side is a certain number with the units place being 3. Is a certain number with units place being 3. And the right hand side is square of a natural number. Right? Are you there with me? Now, this m is a natural number. M in its units place would either have 1 or have 2 or have 3 or have 4 or have 5 or have 6, 7, 8, 9. These are the possibilities of the units place of m, or 0 or 0, isn't it? So square of m will have in its units place 1 square 1, will have in its units place 4, 9, 6, 5, 6, 9, 4, 1, 0. These are the possibilities of the units place of m squared, isn't it? These are the possibilities of the units place of m squared, yes or no? Right? So then m square will end with 1, 4, 6, 9, 5, 0. M square will end only in these numbers. Can m square end in 3? M square will not end in 3. That means this is not possible. I can't find a natural number n whose square ends in 3. So there are no natural number solutions to this in m and n satisfying this condition. Are you there with me? Right, Utsav? I can't successfully find natural numbers m and n that hold on to this condition, Right? So that also is simple observation. It didn't require rocket science. It didn't require sophisticated results. All that it required was simple observation, trying to check things from what you've already learned till this point of time. Clear? Be confident about what you've learned, because every single problem on the planet can be done from first principles. From whatever you have learned till your class 10 or till 9, everything can be done. You can go ab initio, attack the problem. Without being equipped with too much knowledge, you can still solve the problem, as long as you are willing to be present in the problem. So far so good. Have you registered the thought here? Right? I'm just trying to build you up for this thinking. I know you have not had enough exposure to this, but all that I intend to do by means of this class is to give you this extra veneer of exposure that allows your brain to open up to these things. All right. So even if you're not able to independently solve these problems, does not matter, but at least your brain will start getting attuned to this frequency. Clear? Okay, so let's give ourselves a chance to look at problem 3 then. Let's give ourselves a chance to look at problem 3. Even though some of these problems might look exotic, might look esoteric, trust me, they are all within the reach of the basic foundation that you have acquired till this point of time. It will not require too much of sophistication to be able to do this. Just basic first principles. Let's enjoy this, okay? Don't feel burdened with this. If you can't solve it, no issues, but smear yourself in this thought and see the pleasure that you get out of this. That's all that I want you to do. Fine, shall we move? Right? I know I'm holding on to you in the sense, causing you to be passive right now, but this being your first stint with integers, I'm trying to, help you get into the groove rather than, push load on you. Okay, let me explain the next problem. Let me explain the next problem to you. What's given in the next problem is A and B are odd integers. Odd positive integers. And see, if A and B are odd, their difference will always be even, isn't it? Their difference would be even, but need not necessarily be divisible by 4. It will be divisible by 2, but need not be divisible by 4. Right? So what's given in the problem is, even though A and B are odd, and surely A minus B is even, but they say that A minus B is not divisible by 4. That's given. Not divisible by 4. That's the condition offered in the problem. Huh? Let's see. Hey, switch it off, switch it off, switch it off. Two things. Yes, all of you must change your ringtone. It's not very soothing to the ear. All right? Next time, if it rings and I find the same ringtone, then you will be in for tough times. All right? Change your ringtone. Don't have such a harsh ringtone. Not like one of the students, whose phone rang and it said, washing powder Nirma. I said, what? Suddenly this ad, I realized that was a goddamn ringtone. Your generation is very exclusive. All right. So these are two conditions given. A, B are positive odd integers, and it's also given that A cubed minus B cubed is 2 to the power n, where n is a natural number greater than 2. N is a natural number greater than 2. N is a natural number greater than 2. I want to be able to find values of A, B and n. I want to be able to find values of A, B and n meeting all these requirements. Right? A, B are odd positive integers. For sure A minus B will be even. I can't stop that. If they are odd positive integers, I can't stop. And I will also assume that they are distinct. I will assume that they are distinct. Okay. If they are odd positive integers, for sure what can't be changed, if A and B are distinct, is that A minus B is even. Is the fact that A minus B is even. That's certain, right? The difference between any two odd numbers will always be even. All of you understand this, isn't it? Okay. Now, let's look at A cubed minus B cubed. What would you want to do if you are given an expression like A cubed minus B cubed right away? What would you want to do with this? Eat it up? Factorize. Factorize, yes, you want to factorize A cubed minus B cubed and see what transpires, right? So, let me factorize A cubed minus B cubed. So, I am in the first place examining the feasibility of this occurrence. Whether A cubed minus B cubed could be written as a power of 2, where this power is greater than 2. Can that at all happen or not? Let me examine that possibility. How's that? Now, A cubed minus B cubed could be looked upon as A minus B. All of you know how to factorize this? Huh? A square plus AB plus B squared. Ideally, I would like abundance of a minus b in the expression. Why would I want abundance of a minus b in the expression? Because I have knowledge of a minus b. I know that a minus b even and a minus b is not divisible by 4. So to generate abundance of a minus b is my first objective. Now, you really think it will be even? Let's see. Supreet, see, this a square plus b square I can write as a minus b whole squared plus 2ab plus ab, that makes it 3ab. Yes or no? This a square plus b squared I can write as a minus b whole squared plus 2ab and plus ab, that makes it 3ab. Supreet, this is how it is. A square plus b squared I can write as a minus b whole squared plus 2ab. So a squared plus b squared plus ab, which is the other factor, this one is like a minus b whole squared plus a 3ab, right? So can't it be 6? See, let's see. All right. This for sure is even. A minus b is even. Right? This factor is even. This one, a minus b is even, so a minus b whole squared is also even. A is odd, given. B is odd, given. 3 is odd for sure, so this is odd. So even plus odd, what is that? Odd, right? Yes or no? So then this a cube minus b cube that we have is like an even number which is not a multiple of 4. This is an even number, not a multiple of 4. Is an even number into an odd number, where this even number is not a multiple of 4. This even number is not a multiple of 4. Is it not? It's even, but not of the form 4 into k. It's not of the form 4 into k. It's not divisible by 4. Okay. Now, so far so good, right? Huh? Now check this out. Which means this product, even though it will be even, it will not be a multiple of 4. Why? Because I hope you realize that this is an odd number. It will not contribute 2 in the factor, and this will contribute 1 2 in the factor, but not 2 2's. It will not be divisible by 4. Yes, absolutely. That means a cube minus b cubed is not divisible by 4. Is not divisible by 4. What do you say? Is not divisible by 4. Why? I hope you realize that. This is not divisible by 4. This is not divisible by 4. So the product is not divisible by 4. This is an odd number. It will not give any 2's. This is an even number which will give me 1 2, but not 2 2's in the product. Because if it had given me 2 2's, it will be divisible by 4. But that's not the case. So that means this product is not divisible by 4. A cube minus b cube is not divisible by 4. Right? And 2 to the power n for n greater than 2 will be at least having 2 2's and other 2's. So it will have 2 to the power n if n is greater than 2. If n is greater than 2, then 2 to the power n will have at least 2 2's and some more 2's maybe. At least, isn't it? At least 2 2's. That means this is divisible by 4. If n is greater than 2, 2 to the power n will be divisible by 4. Yes or no? Right? So 2 to the power n is divisible by 4. So do you think this is a viable proposition? Left hand side not divisible by 4, right hand side divisible by 4. So this possibility is ruled out. I can't find A, B and N meeting the requirements of the problem. Does it make sense to you?